All right, welcome everyone. If you're gearing up for the CSIR-NET exam, you already know that population ecology is a massive, high-yield topic. Today, we're going to master the two fundamental models of population growth. We're talking about the engine of life's potential versus the brake of reality. Let's dive right in.
So here's our game plan. We'll kick things off with the absolute fundamentals. Then, we'll journey to the ideal world of exponential growth. And right after, we'll contrast it with the real world of logistic growth. We're going to uncover what I call the ecologist's golden rule, a lifesaver for your exam. And we'll wrap it all up with a blueprint for success. This is going to be your roadmap from just knowing the theory to being totally exam ready.
First up, the fundamentals of growth. Getting these core terms down is the absolute foundation for everything else, so let's make sure they're crystal clear before we even think about those curves.
Okay, so what's really cool about this is how simple it all boils down to. N is just our population size, T is time, pretty straightforward. But really, the star of the show here is R, the intrinsic rate of increase. Think of it as the raw biological engine of the population. And here's a huge exam insight. For these models, we assume a closed system. That means R is just the birth rate minus the death rate. Simple as that.
All right, let's take those fundamentals and plug them into our very first model. Welcome to the ideal world of exponential growth, where we get to explore the absolutely explosive power of life when it has zero limits. And here it is, the famous J-curve. This thing represents pure, unfiltered biotic potential. Imagine ideal conditions. Infinite resources, no predators, no disease. The population doesn't just grow, it accelerates. The more individuals you have, the faster the population just explodes upwards. It is life completely unleashed.
And you know what? The math behind it is just beautiful in its simplicity. The rate of change, dn over dt, is simply equal to r times n. What does that really mean? It just means the speed of growth is directly tied to how big the population already is. The bigger n gets, the faster it grows. It's a complete runaway feedback loop.
So you might be sitting there thinking, okay, this is just theory, right? But we actually see flashes of it in the real world. Think about bacteria in a brand new petri dish, or a sudden algal bloom that chokes an entire lake, or even a terrifying swarm of locusts. These are all real-life examples of exponential growth. But, and this is a big but, here's the reality check. This state is always temporary. It just can't last.
So that brings up a really important question. Why don't these J-curves last forever? If this kind of explosive growth is possible, why isn't the whole world just covered in bacteria and insects? What's holding them back?
Well, the answer comes down to one single, incredibly powerful concept: environmental resistance. See, as that population just skyrockets, the environment itself starts to push back. Competition gets fierce, predators take notice, diseases spread, and you just run out of space. This combined force is what connects the dots between that ideal J-curve and the reality we actually see in nature.
And that, right there, brings us to our second and much more realistic model, logistic growth. This is where that raw potential smacks into resistance, and what you get is the incredible balance we see in nature.
So instead of that J, we get an S, the classic sigmoid curve. It starts off looking almost exponential, but then it starts to bend and flatten out. And that ceiling it hits, that is probably the single most important concept here. We call it K, the carrying capacity. It's the absolute maximum population size that a particular environment can support over time.
Okay, so how does the math actually describe this? Look at the equation. We've still got our exponential engine, that Rn part. But now it's being multiplied by what I love to call the brake pedal, the environmental resistance term. Think about it. When the population n is tiny, that brake term is basically 1, so the foot's off the brake. But as n gets closer and closer to k, that brake gets slammed harder and harder, slowing everything down until it just stops.
And this gives us a perfect picture of the whole life story of a population. First, you've got the lag phase, where it's just getting settled. Then, boom, it hits the log phase, growing like crazy while everything's perfect. But then, as resistance starts to kick in, it enters the deceleration phase and things start to slow down. And finally, it hits the stationary phase, just kind of hovering around that carrying capacity, K, where births and deaths are pretty much in balance.
So, let's talk more about this carrying capacity, this K. What is it really? Well, it's not some magic number that's set in stone. Think of it more like a dynamic ceiling that the environment sets. In a pun like this, it's about the amount of food, the available oxygen, the physical space, even how fast waste builds up. You change any one of these things, and you change K.
Okay, everybody, listen up. I mean it. We have arrived at the ecologist's golden rule. If there is one single thing you take away from this whole session for those tricky Part C questions, this is it.
So here's the rule. The population's growth rate isn't fastest when the population is biggest. No way. It's actually fastest at exactly half the carrying capacity, when n equals k over 2. This is the sweet spot, the point of maximum sustainable yield, where the balance between population size and resources creates the biggest possible jump. I'm telling you, this is a classic CSIR-NET question. They love asking about this.
Okay, let's bring this all together. Think of this next part as your final exam blueprint. We're going to wrap up everything we've just talked about into a super powerful summary for your revision.
All right, let's put them head to head. On one side, you've got exponential. That's the J-curve, unlimited resources, totally unstable. On the other side, you have logistic. That's the S-curve, limited resources, and it finds that nice stable equilibrium. And here's the absolute key difference for your exam. Exponential growth peaks when the population is biggest, but logistic growth, it peaks at k over 2. This table right here is your ultimate quick glance guide.
And if you want it even simpler, here it is, your ultimate revision tool, the CSIR-NET cheat sheet. For the models, it's easy. Exponential is the ideal world, logistic is the real world. For the math, just remember it's all about that environmental resistance brake pedal. And that golden rule, if you see any question asking about fastest growth or maximum sustainable yield, your brain should immediately scream k divided by 2.
So let's end on this image, because I think it captures the entire story perfectly. That plant's unstoppable drive to grow, that's its biotic potential, it's R. But the concrete pushing back, that's the environmental resistance, the thing that sets the carrying capacity, K. So if you walk away with one final thought, let it be this. Exponential growth shows us life's incredible potential, but logistic growth shows us the environment's immense power. You understand that balance? And trust me, you are going to be more than ready for your exam.